So this is another example again, like you see, right? This 11001010. So if you want to change it into decimal form, always remember this. You just put a 2 power of 0 starting from here and then go all the way there. Alright, like you see over here. This is an example for you, and you just add those up together. It will give you 202. Equivalently, this is for point form. So when you have point form, remember over here you start with 2 power of negative 1 for this bit over here. Alright, then this 2 power of negative 2, 2 power of negative 3, and 2 power of negative 4. Multiply them together, sum them all up. This is what you get. Alright, and make it a habit to write down the base. I think you guys are pretty much good at this by now. Alright, we have looked at the binary form to decimal conversion as well as decimal to binary. Alright, now that you are familiar with this, just like I mentioned before, if you are doing anything else, whether it's base 16 or base 8, everything goes the same way. Alright, so this is just a representation of how things are, alright, in its decimal form and its equivalent binary form and hexadecimal form. Alright, if you remember, we have looked earlier on, actually for decimal and hexadecimal, everything stays the same up until 10, where it's expressed as A, B, C, D, and E, F, up until 15. Alright, so literally it depends on what you use. In this case here, sometimes for hexadecimal conversion, you notice, right, everything stays the same, but you may have something like A and F. So it's always important for you to know that it stops at 9. A literally means 10. So if you want to know what F is and so on, you just take A as 10 onwards, and you just do it as you count it increasingly, like A, B, C, D, E, F. Alright, so B will be 11, C will be 12, and so on. Alright, so like for example, this is 2AF. Alright, what you do is you change it into its equivalent form, because A is actually 10, F is actually 15. Alright, how you do the decimal conversion? The same way like what you did just now for base 2, alright? Because for base 2, you take 2 power of 0. So in this case, because this is hexadecimal, alright? You want to change it from hexadecimal to decimal. So look at the base, it becomes 16 instead, alright? 16 power of 0, 16 power of 1, 16 power of 2. Add those up, your final answer will be here. Just the same over here, right? Remember just now from decimal to binary we do the division, right? So this one exactly the same, only that you divide by 16. Alright, your remainder is 7. Alright, but like for example over here, when you have 26, you divide by 16, you get 1, but you see the remainder is actually 10, right? Then just recall back, for hexadecimal, 10 is represented as A. Therefore, you have an A here. Alright? And lastly, over here, do give it a try though. Alright? On a piece of paper on your own. Alright? And like I said, you always go by bottom all the way to the up. Alright? So that's why it's 1A7 base 16. So this is the same. You can see that every style is basically the same, only that you might find it a little funny at first if you are looking at it the first time, that hexadecimal has things like A, C. So basically you just need to remember A is always 10, alright? So if A is 10, B is 11, C is 12. That's why you see that over here and here, this is actually 12. Alright, for you to do the conversion and all that, you just literally need to know what this alphabet stands for. Then you can just do the equivalent conversion as usual. Okay, so there is a shortcut way for you to do hexadecimal to binary. Okay, so what happens is that, like for example, this is 3, 9, C, and 8. in the case where you want to change from hexadecimal to binary, okay, look at it here. You just write down a 4-bit binary code. For example, 8, if you look at your binary equivalent, is actually 1000. Your C is actually what? A is 10, right? So B is 11, C is 12, alright? The equivalent binary number is here, 9 is the same here, and 3 over here, alright? And then you just group them up together, the same as this one over here. A is 10, 10 is represented as 1010. So we are talking about from hexadecimal to binary, yeah? So this is hexadecimal, whatever that you see of the 0 and 1s, these are the binary equivalent. So what it literally means is that you can directly convert it into its equivalent binary form, but always remember it has to be in 4 bits. For example, like 3 here, you know that the equivalent is actually 11, but you always write it down in terms of 4 bits. So that's why for anything that has no value at the front, you just fill it up with 0. Therefore, it becomes 0011. Alright, so basically this number here of base 16, the equivalent binary form is this one of base 2. Alright, I hope you understand this part here. Just the same, alright, just now we look at hexa to binary. If binary to hexa, still the same, you always go by the rightmost side, which is the least significant symbol. Alright, so you group it up in terms of 4. Alright, 4 bits by 4 bits, and then you just look at the equivalent of what it literally is, then you change it into its equivalent form in hexadecimal. Like for example, E here means what? If you look at the binary form, so it literally means that this is, I think, 14, because A is 10, so B is 11, C 13, D 14, 11, 12, 13, yeah, and then A, B, C, D, E. E would be 14. Alright, so if you look at this, the equivalent, then you just change it into its equivalent hexadecimal form. Just the same as this one, alright. This is 10 actually, but in hexadecimal we do not have 10, right? We have it as A. Alright, same goes here. F is actually 15. So this is actually 15. You take 2 power of 0, 2 power of 1, 2 power of 2, 2 power of 3, add all up together, you will notice that this is actually 15. But for you to indicate 15, it's actually F in its hexadecimal form. So for binary to hexa or hexa to binary, it literally is pretty much straightforward. You just group it, you can see that it's a group of 4. Alright, so do give it a try. Now we go with octal system. Alright, octal is the same, alright, but we see a direct relation between binary and hexadecimal. So like for octal, just the same, but instead of 3 it becomes instead of 4 binary digit, it becomes 3. Alright, you have a look at it over here. Okay, convert octal to binary. So like I said over here, this is the octal form. Okay, 635.17. So this octal, because it's base 8, alright, if you want to change it to binary form, just now for binary and hexadecimal, it's 4, right? 4 digit. So for octal, it's 3 digit. Alright, you can see that it's 3 bits, and so on. Okay, just the same. What happens when you have a string of number here? Alright, you always divide it by the point form here. Alright, then you go by 1, 2, 3. Alright, so this is from binary to hexadecimal. Alright, so 1, 2, 3, 4. Alright, so that's where you get 0011. Alright, when you get here, this is 1110. So this is 1011 for this part here, 1100 over here. Alright, and then for this one, you add another 3 bits at the end. Alright, So basically you divide them into 4 starting